All right, now that we're on to the third video of this series, let's take the knowledge that we learned about PowerPC a few minutes ago, or however long you watched this ago, and let's translate this to working to a game. So the first part of this tutorial is going to be concerning setting a write breakpoint. By setting a write breakpoint, we find what actually modifies a particular address in game memory, which shows us the code that is actually making the change. This allows us to find where that code is, modify it, and thus change the game's behavior to basically whatever we want it to do. Whenever we set the breakpoint and the breakpoint catches, you will see the console freeze. That is normal. It freezes it so it actually shows you what's going on in real time in memory. So usually an instruction only writes to 1 to 2 or so addresses, but this can vary depending on the game. I've seen an instruction write to like 1,000 different things at once. I have seen that before. Keep in mind that several instructions may write to one address, so you may have to comb through several instructions before you find the right one, or you might even have to change multiple. Beforehand, I had you looking in the CO to DF memory range to find where your values are. That really only works for statics. We cannot set breakpoints on those memory regions for whatever reason at all. Fortunately, these addresses are mirrored somewhere else in memory where a breakpoint can be set. The bad news is this is going to take a while to find out where it's mirrored. You're going to have to check out every single memory region. I'm not kidding. It's so from 0 to B and then potentially E to F. Though I've never seen anything of importance there, so likely just 0 to B. In other games, I've also never seen this, but I've read it occurring online. In other games, sometimes the C memory range is mirrored directly at the A range, and sometimes the D memory range is mirrored directly at the B memory range, allowing for you to set breakpoints on those. Honestly, not the case of every game. It hasn't been the case of any single thing I've tried. So try to see if those two are available first, and if they're not, then go for the OX4 range, and then you can try them from an order from 0 to B and then E to F. So because I have played around with this game a lot, I know ahead of time that the range is mirrored in OX4. So here's what we're going to do. Let's set a write breakpoint on our ammo address in Resident Evil 4 to see if we can make our guns have infinite ammo. Okay, so here's what I'm going to do. Take a look, go to allocate, scan, and these are all the memory regions you can see are available. We have region 0, 3, 4, 7, 8, and 9 for Resident Evil 4. Other games' memory layouts will be entirely different. It's just based on however the programmers wrote the game. Taking a look here, as I said, I know it's the 4 range, so I'm going to start out at 4 and then grab the end of 4 right there so we don't have to search needlessly for multiple things. And now I'm going to search like we're trying to find our ammo all over again. So we're going to do an initial search here. We'll take a little while to find it. And by the way, I'm taking the hard part out for you, but as I said, I know it's in the 4 memory range. For your game, if you don't know how it works, you're just going to have to test 0 all the way to 0F, 1 to 1F in the same repeating pattern all the way up. Yeah, it sucks. I'm sorry. It is what it is. Okay, so now let's see. Going to click exact. Hopefully We're able to find this relatively quickly so we can move on to other examples. Okay, I can fire off a few bullets. Okay, we're at 27. Let's do another search. All right, that's narrowed things down quite a bit. Let's shoot a few more. Okay, there we go. There is where our memory address currently is. So how do we set a breakpoint? Well, I'm going to open Microsoft Visual Studio 2010, and I'll show you how to do that. By the way, I'm going to pause the video and refresh it for a quick second because it shows my personal email address when I open this tool. I ain't showing that. All right, so here we go. You've opened the Visual Studio 2010 tool. You click Debug, Attach to Process, Xbox 360 debugging, you choose your IP address, choose the game, and that has us connected. So what do? First off, we click pause on the game. Notice how the second I pause the game, it's completely frozen. That is completely normal behavior. Your game is not crashed. I'm going to go to new data breakpoint, and I'm going to copy this address in and put an OX in front of it here. Then remember how I assumed that this was an 8-bit or a 1-byte value? Well, I'm going to set the byte count to 1. That's kind of why that's important. You need to know how much is being written generally. Okay, now I'm going to click play on the game again. Notice that the game starts back up. Now I'm going to fire off a bullet, and it should get tripped the second I fire even one. See, the following breakpoint was hit when this address changes. Taking a look right here, it looks like the instruction at the address 8232FFFC is the one that controls AMO in this game. So let's say I want to see a little more. Come up to this register box up here, right-click, control, right-click, integer, right-click, floating point. That gives us all the general registers I told you about earlier. Now, to kind of show you what I meant by D plus RD equaling your address, let me show you that here for a quick second. So if we go to register 30 right here, which is the RD, and then we add it by D, the 8 there, we see that our address is 404D8CA2, which is one off from our current one, and it turns out I actually thought that this was a 1-byte value, but based on what I've seen here, STH, half word, it's a 2-byte value that's controlling the whole thing. So that kind of shows you a little bit of what's going on there. That actually did pinpoint the exact address we were looking at. And if we look at R10, we fired one bullet. We were at 25. So it should contain 24. So I go here, take a look at that 18 in hexadecimal character. Oh, look, it's about to write 24 to the address where we just shot. So that is exactly how that works. Replay the game gets released. Interestingly enough, there is some uses to what we would call an execute breakpoint. You remember how I said, so let's go back to the PowerPoint here. Execute breakpoints allow us to set a breakpoint on a specific line of code watching it execute in real time. This is useful for allowing us to see what's going on in code, helping us to find problems in our own code, and it also helps us to find where the current address of interest is. So I showed in the last video that Resident Evil 4 has a different address for each gun value. It turns out that this instruction right here controls every single gun value in the game. So by tracking what this does, we can find every other value indirectly. So let's take a look here. Crap, I forgot to disable it. Disable it if you're not using it, or else it'll just trigger a million times. Okay, so let's say we wanted to find where the Killer 7's ammo address is currently stored. From what I told you, it's stored right here. So let's pause the game. It's already paused. We click off to the left-hand side of where that address is. That sets an execute breakpoint. And now we just shoot the gun in game, which triggers the breakpoint, causing the code to run. As you can see, currently that executed. And if we take a look, pop this into our calculator over here at R30, add 8 to that, and oh look, the address for our Killer 7 ammo is right here. We can also see some other gunk that's going on in these other registers too. These really aren't that important right now. But, I mean, it's here. Now, why does any of what I said matter here? Like, what is the point of all of what I just said? Well, you can actually change this code to make it do what you want. And I'm going to show how we would do that. I'm going to disable the breakpoint. And I'm going to go up here. See right here where register 10 is being used and modified? We can just take what's in register 10 and change it to what we want and get rid of whatever this instruction is. So let's go right here. You remember our load immediate instruction that allows us to set whatever R10 we want to be? So I'll put li R10 7F, and I want to make my gun shoot 127 bullets. Okay, that's what that compiles to in hex. Go here, open PeekPoker. Here, 4, and that is the current code that is written. Let's write the new code in and see what happens. 3940007F, poke. Okay, now we unfreeze the game. And now let's take a shot. As you can see, 127 bullets. And not only does this work for the one gun, but it works for everything. Because we changed the address, because we had changed the instruction that controls ammo in the game, this will now affect almost every single gun in the game, being a way to have infinite ammo without having to always find the address each time it changes. Another thing that we could have done that would have also accomplished the same result would have been to go, except for changing the number, of course, would have been to go where this address is right here at 8232 and set this to no operation, which means that it just does nothing. So if I typed in nop right here, you can see nop equals this 6 value. So we type in the 6 value right here. And now, because that instruction has been completely destroyed, now you're not going to see our ammo go up to 127. You're just going to instead see it not change. All right, so that is one example. Let's take this up a notch. And by taking it up a notch, this is going to go up quite a bit in complexity. What we're going to do now is learn how to make something known as a code cave. Remember how I said the game has functions? We can make our own, and that can make it easy to hack the game. This allows us to make our own functions. This is especially helpful if we don't have enough room to do what we want without breaking the game. If there hadn't been an instruction containing R10 right there, I would have had to code cave, then put a load immediate in, and then code cave back. So here's how you do this. First off, we got to know how many instructions our function is going to be. Assuming your function has 3 instructions, each instruction is 4 bytes, so you're going to need to find 12 free bytes in memory. So what instruction am I talking about here? Well, I've got an idea of one to make. This instruction at this address right here, let me see if I can remember it. Oh, there it is. The instruction at 82399B5C controls what item we get in the shop. See this right here? That is actually going to control what item we really end up buying. Notice I do not have enough room to do anything here. There's a lot of branches, a lot of compares. I don't have the space to just pop something into register 27 without breaking the game. So, to get around that, let's say I wanted to make the item anything. I don't know. Let's say we wanted to make this the first item in the game, whatever the heck that is. I can't remember. Okay, so that is the function that we're going to write. Why are we writing this? Well, I'll show you. So this is the address we're going to. As I said, we need to find free space. So let's find a place we can put some free space in. So to find a place for free space, first off, you're going to go to allocate. We're going to take a look here. Okay, 82, that's the starting address of the default XEX range. And the 82F7 is going to be the end of the default file. Okay, so we take a look here, set this to 4 bytes, set this to 4 bytes, set this to 0, do an initial scan. Okay, we need the load immediate to set the value to whatever we want. We need the store instruction to make the item whatever we want. And then we need to go back to the game's code, else the game's just going to stay frozen forever. If you don't change it back from your code to the game's, it's just going to crash. So let's see how we do that. So just click initialize here. It should go pretty quickly. Hit exact 0. And now all we need to do is find an area that has 3 consecutive bytes in a row that we can take. I mean, not 3 bytes, 12 bytes in a row. Okay, so 82020, 82024, 82028. Okay, that's 4 bytes, that's 12 bytes right there, which is exactly the amount that we need. Let's start from here. So let's say we're going to write this new code right here. Okay, so here's what we got to do. We got to use a branch to get us from where the original code was to our custom code, and then we got to branch back, which allows the game to run again as per normal. So here's what I'm going to do. I'm going to calculate the amount of distance that it has to take there and back. So let's say I want to go from 823 to this 8220. I pop this over in the calculator here, subtract that out. Okay, the distance we need to do is that. And considering this number is greater than that one, and we're needing to go lower, we do a subtraction sign. So negative OX 399B3C. And now our last instruction is 8228, right? So what we need to do is we need to do the calculation to get us back plus 4 of the original. So what we need, so it doesn't just run over and over and over again until the game just never does anything. So we need to get back here. So now let's calculate this distance. Okay, and this is, this is in the positive direction because this number is smaller than this one. So 399B38. All right, and basically what this is going to do, this is going to subtract this number from the program counter and force the program counter to start here. And this is going to add to the program counter, forcing this to start here in the code. So now, how do we get this in? Well, first off, we got to compile it. Make sure you've, when you're loading PyASMH3, you have it set to raw code type instead of anything else. That just gives you the bytes. This is originally used for the Wii. That's what all this other crap is, but we're not on a Wii, so it doesn't matter. Okay. Copy in all the crap that we pasted here. Boom. That is what all of that says. So this will make our new function. And how do we put the new function into the game? Well, that's actually pretty easy. Go here. We were using 12 bytes, right? So just type that in hexadecimal, which is, okay, it's not going to let us do that. I don't know, just type whatever you can get. Okay, and now what I do is I start at 8220 and I type all this garbage in. 3B, 60, 0001. B3, 70, 0010. 4839 9B 38. Now I click poke. That goes right to the game. And now what we have to do? Sure, that puts our function in game, but it's not going to get called. Not unless we make it get called. So how do we do that? We make this last one here. Go to this address. And then we paste in what was generated there. We poke. And now we run the game. Whenever I buy an item in the shop, it shouldn't matter what item I buy now. It should just give me the item of my choice. So let's say I buy, I don't know, first aid's mass rifle scope. And what do you know? 01 corresponds to a grenade. So even though we bought the scope, we got the grenade like we wanted. Cool. Shows you that what I did actually works. And let's do something a little smarter here. What if we wanted to see how our code works in real time to see kind of what's going on? Well, sure, let's go right ahead. go to where we placed it. This might not have updated, by the way. It's still saying that, but trust me, it's changed. You'll see. So I'll set an execute breakpoint, and we'll watch what happens as I go and buy another item. The second I clicked on the item, the game froze. That's because it's called the breakpoint. Now I can step into this, like click step into right up here, and that sees, okay, so yeah, this is all that code we wrote here. So as you can see, R27 was 23, the value of the handgun. So it was trying to give us a handgun. Okay, load immediate runs, changes it to the value of the grenade. STH runs, storing it to the game. The branch runs, getting us out of the custom code, back into the game's code. And then as a result, the grenade. Okay, so now that you've made your first code cave, I'm going to teach you how to set the final type of breakpoint, a read breakpoint. Sometimes the game will read what value is at an address for varying reasons, such as comparing to see if you have enough money for an item. For instance, you could load the cost of the current item and then load the current money that the player has by doing a comparison to see if the player's money is greater than or equal to the cost of the item. You would let the player buy the item. Otherwise, if it ended up being less, you would prevent the player from buying the item. And by setting something like a read breakpoint, we can actually find where the game is reading that into memory and sometimes even doing the comparison at. Now, to tell you the truth, I seldom use read breakpoints, but I had to use this type of breakpoint extensively for the Borderlands game series, because it turns out their store instructions not only wrote to one value, but literally everything in the game. By changing a store instruction for ammo, I'd often find that I was changing time, health, and gravity all at the same time. If you get a strange game that kind of works the same way Borderlands does, this can help you get around that issue. So kind of harping on kind of what I was going to talk about skill point comparisons or like money comparisons, let's take a look at Resident Evil 6 here for a quick second. I'll turn the game volume back up now that I'm no longer giving a presentation. So through some shenanigans, and by shenanigans I mean setting an execute breakpoint, I know the address of my current money. It's right here. So how would I set a read breakpoint on this? Well, what I do is I open XCE tools. Strangely, you can't actually do this from Visual Studio. You have to use XCE tools to do this. But basically what you do is just make sure Visual Studio is open, by the way, because if it's not, you're not going to see what's going on and the game's just going to freeze for no reason. So you take your address, paste that in, set the length of the bytes. I know this is a 32-bit or a 4-byte value, so I'm going to keep it to that. And then you see this drop down, none, write, and read write. You're going to set it to read write. Unfortunately, that means you get store instructions as well, but that seems to be the only way to get the read instructions at this point. So I'm going to set the read write here. And something you'll notice very quickly about read addresses is a lot of times they will pop nearly immediately and over and over and over again because the game is constantly doing checks against that value. If it wasn't doing checks, the player might be able to slip through and make a purchase they shouldn't be able to. So taking a look right here, that is exactly what seems to be going on. So taking a look here, watching it load, let's run it step by step. So this instruction was what was reading the current one. Okay, so that ran 1E14 into R9. That's the value 7700 right here. And then oh, this is actually not the one we were looking for, funny enough. How do I know that? Because I've screwed with this game before, and I can tell you as a matter of fact that that is not the correct one. A lot of times what you're going to have to do, though, is you're going to have to copy down which read breakpoints you get, NOP the read breakpoint, and then continue until you no longer get read breakpoints and continue writing each of them down. And the reasoning behind that is you can often find yourself with multiple read breakpoints doing multiple things. So expect to be here a while when it comes to this. So, okay, I've notched that now. That breakpoint is no longer hitting. Now let's say I press A. Oh, look, the breakpoint actually triggered. And this time, as a matter of fact, I can tell you that this is the correct one. So if we take a look right here, this loads the player's current money into register 9. And then R10 ends up being the cost of the current item that we're looking at. So the current item that we're looking at is 3,200, right? So take a look, 3,200, C80, yep. And then it's going to say, okay, branch if less than or equal to. If R10, the cost of the item, is less than the amount of money the player has, then branch to this instruction right here, allowing for the completion of the purchase. Otherwise, skip and go further on. That's an example of what a read breakpoint might show you. And as a result, now we kind of know how the money instructions work in this game. I literally only know that that's the appropriate one because I've tested each individual one to see what one did it. The first one, now that you can see the value set to 0 here, seems to have been taking a look at the visual skill point address, whereas this one was taking a look at the difference between the items, it seems. So then what I could do is I could either change this load word 0 this to li r9 and then whatever I want, which would always give the player's money as having a higher value and thus always force the player to be able to purchase the item. Or I could just change the branch to always pop no matter what. So I could do this either by, typing li r9 then ox, just like, let's say I just give the player 2 billion. Or I could do this by just coming down here, looking at that branch. Okay, that branch is branching 10 forwards. So that's a BLE, it's 10 forwards. So I just would type in BOX10, and then this gives me two options. I could either go right here to this address, paste this in, that 3D 220, or I could paste the different branch in. Regardless, so here, for the sake of all this, I'm actually going to paste the different branch in and hope that I haven't majorly screwed this up, because I might have. 48000010 poke peek. Okay, Now, here's what you need to do. When you know you found the correct one, come back here, click None, and then click Set 1 or 2 times. Because if you don't, and literally anything writes to it again, or you write to it, the console crashes, and then it goes through this loop of where it takes forever, and then you have to re-download your avatar update. It's annoying. I'm just warning you ahead of time. I've had it happen to me several times. So let's say here that I only have one bullet or however much. As you can see, even though I don't have enough money to purchase it, because I changed that branch, it's letting me purchase it every time anyways. Because it's no longer seeing that I have less than or equal to the amount of money. Now it's just executing it regardless. So that is an example of the read breakpoint. I'm kind of going to go back to the dashboard here, and then I am going to go right back into the PowerPoint. So we have another quite complex topic before we finish off. This is going to be shown through 2 examples near the end. This topic, we're going to be talking about the stack and manipulation of the stack. The stack is where extra values the game is storing for later is stored at. The address of the current location in stack, the game is that is a giant typo. Anyways, the address of the current location in stack is stored at the SP, the stack pointer register, which is also known as S1, as R1. Think of the stack like a stack of papers. In a giant pile of papers, or a giant stack of papers, the first paper in the pile is at the bottom. And thus, if you were to start at the top and start pulling papers from the top, the first paper that was placed in is the last one that would come out. Vice versa also ends up being true. The last paper in the pile is at the top, and thus it would be the first paper out. This gives the stack what is known as FILO, first in, last out, and LIFO order, or last in, first out. As a result, this ordering of the stack allows us to place items at the top of the stack, access them later, and then remove them. This allows us to restore the stack to how it was so the game can use it normally. And a lot of the times, the reason we would need to modify the stack to begin with is you might find that you've got 32, your 31 GPRs, right? But they're all being used by the game. And if you destroy one of the values in those registers, you might find an instruction needs it later, and then that ends up causing the game to crash. So if you're see that you don't really have a free register to work with, this can kind of free one up so you can use it for whatever you want, and then basically restore the register to the way it was before you messed with it and have everything you needed to have done. Backing up the registers to memory is called a push. A backing up registers to the stack is known as a push operation, and then removing them from the stack and restoring them is known as a pop operation. So for push and pop, basically, as I said before, when you push, you store some registers to the stack to reference later in your function. When you pop, you remove them from the stack. 90% of the time, you can use the code from example 1 and it'll work. But sometimes this will cause a stack overflow, crashing the game. I give several examples after this. Basically, these are just lines at the beginning and end of your code that you can copy to free some registers so you can do what you need to. You're not going to need to do this with every code. You're just going to need to do this with things if you need to do like comparisons or you need to store something and you don't have space for it. But anyways, the problem is the more that you store to the stack, the greater you have a chance of overflowing the stack. Imagine the stack of papers sort of falling down after you've, built the tower up so high. That causes the game to crash, by the way. To avoid this, you can minimize the amount of things that you push to the stack, which you can do with pre-made instructions that I've kind of listed in the next few slides. Usually, I only need to push or pop about 2 to 4 registers at a time and nothing more. I've never really needed to back up more registers than that. I don't know why. You would need multiple, at least for that, but hey, if you need it, you need it. I honestly didn't understand how the stack or how these instructions worked at all at first, and I had to find some information from a link. I got it from Vega at MarioKartWii.com. The link I used to kind of learn about stack manipulation is here, if you want to check that out. So this is an interesting instruction. And this is also a bit of a typo that I'm going to go back and fix. So here's what. This push right here, the first 2 instructions that you see make up the push. The last 2 instructions make up the pop. The random instructions in between are whatever you want them to be. So when these 2 run, this is going to store everything from R3 to R31 to the stack. That means those registers are now free. You can throw whatever you want in them and not have to worry about crashing the game anymore. Then you can execute your instructions in between using those registers for what you needed them to. And then finally, we pop the stack. These last 2 instructions pop it. This allows us to take that R3 and R3 to R31 that we had originally. It restores them to their previous values before we screwed with them. And it frees up the stack for more room. That way the game doesn't accidentally access the extra space that we put on earlier. And kind of the same thing ends up happening. So that frees up 29 registers for you to use. There's no way you're ever going to need that many, but it's there. This option, if you use this the way this is structured, gives you from R14 to R31, giving you 18 free registers. This one gives you 4 free registers. So R28, R29, R30, R31. As you can see, it starts from the register that you give it, and it sort of counts up to 31, is how that instruction is working. And then here's freeing up 2 registers at a time. So R30 and R31 gets freed up, then R30 and R31 gets restored. So why might we need something like this? This kind of might seem like it goes over your head at first, and it did at mine at first, certainly too. But one reason that we might need something like this is, well, you remember how I talked about addresses being dynamic and static? Well, what if you need to find a dynamic address? Well, we can write a function that gives us the address every single time, which would allow us to find where the gun is in memory. So let's actually make a function that does that. And we're going to have to use stack manipulation to do this, because we're going to have to pull a few interesting things off. So here's what I'm going to do. We're going to make a function that finds out where our guns are in game. By doing this, this will allow us to edit these guns later to make them whatever we want to make. That's actually how my trainer, which I did make for this game, works. Is it actually just locates the gun through a bit of code that I wrote. So, okay, let's start up Resident Evil 5. Let's attach to the process. Let's do this thing. So you're going to see why you might need to manipulate the stack here, and it'll become very apparent. Okay, so as you can see, I currently got the SIG 556. What if I wanted to find out where that was in memory? So honestly, I'm kind of going to jump ahead here. The cool thing is after you get the instructions for this, you can just use the instructions to immediately find your address instead of ever having to search for it again. That's what I end up doing, especially when I end up making an example like this, because it feels like it takes forever searching things. I know right here that this is the instruction that controls ammo. So I'm going to find out where ammo is and thus where my gun is. I'm going to set my execute breakpoint. I'm going to shoot my gun. And as you can see, the game is appropriately froze. R4 is this address right here. Yeah, Resident Evil's weird. It stores most of its memory in the 0 region. Resident Evil 5 is weird. It stores most things in the 0 region for some reason. So OX0, that's a very tiny value, but it is what it is. Okay, and then the D value is 8, so I got a +8 to find the real one. Okay, this is where our gun's ammo is currently loaded in memory. Why would I need to find this? I'll actually give you the reason that you need to find this. It turns out that the ammo, no, not just the ammo of the gun, but most of the time, let me rephrase myself. It turns out that in the Resident Evil series games, the ID of the gun, as well as the fire rate and the ammo capacity, are stored right next to the ammo counter. Why is this important? Well, this actually lets you change what the gun is. This lets us edit it, lets us make a few cool changes in game. So as we can see, I know this kind of off the top of my head. It turns out the gun ID is just a few blocks away from the ammo counter, which is right there. So let me show you how I know this. I'm going to type in A right there. I'm going to poke, well, actually, I'm going to unfreeze the game first, or else that could screw things up. I was online, whatever. I don't need to be online. So let's say I click poke. And as you can see, my item changed to a trip mine. Let me change it back. Okay, it's the SIG again. So why would it be important knowing kind of where the ammo counter is? Well, as I said, if we know where the ammo counter is, we know where the gun ID is. And if we know where the gun ID is, we can make the gun whatever we want. This allows us to edit in things like the flamethrower, Wesker's pistol, stuff like that. That's why it would be of importance. Now, let's say for a minute that we want to always find out where this is because we can't just edit that without using that instruction. So I'm going to show you how I do it. So first off, the instruction for ammo was right here. And we know that R4 plus 8 is always going to be where our ammo is. So let's make a custom function here for a minute. And how am I going to do this? Well, I'm first going to register. Honestly, I'm going to steal it from my PowerPoint slides. That's exactly what I'm going to do. I'm going to steal this stuff at the beginning. I only need about 1 or 2 registers for this. So those are the ones I'm going to take. As I said, the push instructions, which are these two, go at the beginning. The pop instructions go at the end. And then everything you want to execute goes in the middle. After these run, we'll have R30 and R31 free to do whatever we want with. Now, let's say what I really want to do here is I want to store the address of the ammo counter so I know around where it is every single time. So we know here that this is the instruction that's going to do it. This is going to store the ammo, but we also know that this right here is where it's going to be. So let's say I want where the ammo is always going to be. I could do Ilmar, R30, R4. Okay, since we backed up R30, this kind of allows us to just put that in R30 right there to use. Okay, add immediate R30, R30, OX8. There. That actually calculates the address that we need. Now the next thing that I'm going to do is I am going to use R31 to do a store operation. What is this store operation going to be? This is going to allow us to store the register to a static place in memory, which would always let us find our address. Basically, if you're familiar with pointers, this lets us make our own custom pointer to put into memory. And by doing that, we can always find where the ammo value is. Now, this is around what it's going to look like. I just need to change what this is because that's actually just setting the address right here in R31. Here is the overview of what this function is going to do. The first two instructions here push R30 and R31 to memory. This one's just going to execute and store the ammo to the game as normal. If we didn't have this here, our gun ammo would be screwed up. Next, we're going to take what's in R4, throw it in R30. We don't want to mess with R4 because that's where our address is going to be, but we do want to do a few things to it without actually messing with it. And how do we do that? Well, we just throw it in 30. And okay, here I do add 30, 30 to 8. And the reasoning for this is I'm just including that D value in there. So basically that's going to give me the proper number for the ammo address every time. This listen ORI is going to store 32-bit value or 4-byte value into memory. And specifically, it's going to be the location of free memory where I'm always going to reference. This is going to allow us to pull that from, say, a trainer later on. This is going to make the actual store to memory, with the R30 being that address that the ammo address that we calculated, and the R31 being the free place in memory we found to store it at. These last two instructions at the end are going to do a pop operation, fixing R30 and R31. And then the last instruction's going to be a branch back, because you know we have to code cave into this, and then we have to code cave right back out. Okay, so remember how we found code caves? First off, we went to allocate. Okay, so the default Zex is from 82 to 8319. 82. Remember, same thing here. Set it to 0, do an initial value search. And honestly, when it comes to free space, I just recommend typing in 30,000 because it can be very hard to find what exactly are some good free spaces to use. So I'm going to let this search complete here. But let's take a look and see how many instructions we need for this to work. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, we need to find at least 11 free spaces. That's going to be 44 bytes. But wait, we actually need 12 free spaces. Not just 11, but 12. And the reason why is, remember how I said we're going to store that address to a free place in memory? Well, we need the free place in memory for that too. So let's see if I can find a place that does that. Okay, so 0. Okay, this is first, second, third, fourth, fifth, sixth, seventh, 8, 9, 10, 11, 12, boom. Okay. This can be the start of the instruction right here. I mean, of the function. This can be the end of the function. Well, this can be the end of the function right here. And this can be where the free space is stored. So, okay, now we know what to put in here. 8220 4948. And now we know how to make the branches too. So I'm just going to do the same thing that I did before. Calculate the branch 2 and the branch back. Okay, so that's a subtraction, so we're going to do a negative branch for this. Okay, the negative branch is this, 52, 2380. And then the positive branch that we're going to use to get back will be 8276 6958 plus 4 from the original instruction. And this will get us back 56 2014. And let's compile all of that over here. Okay, that's our code. Now let's get the branch 2 in there. That's that part of the code. Now we go to PeekPoker and write all of our garbage in. So 9421 FF. Sorry for not talking. I am focusing very intently because if I screw up a single byte in this, I could just crash the game. I do not want to crash the game, and I don't want to have to repeat this either. Okay, 4B, A9, DF, C8. Okay, we got the game back now. Now what I'm going to do is I'm going to shoot my gun. It doesn't look like much of anything happened. And that's the point. A well-made code should integrate seamlessly with the game. But if we go to where we said our free space was, oh look, it now contains the address of our gun ammo. And if I went and copied this, you can see 26 in hexadecimal equals 38 in decimal. That is where our bullet was located. And see, look, 127 ammo. So basically, what this function does is it takes the ammo, every time ammo is calculated, it stores where the ammo address is into a free place in memory, specifically 8204948. This right here frees up the space to do it with. This right here gets us the address stored elsewhere so we can use it. This right here gets us the free space in memory. This stores the address to the free space in memory. This undoes all the changes we did to 30 and 31, and then this goes back to the game's code as per usual. So to kind of show you the way that's working, you can actually watch it happen here. I'll set an execute breakpoint, and then I'll fire my gun. As you can see, starts the SP is R1, so execute. Oh look, R1 changed. We're moving the stack. Gets us some extra free space. Back up 30, back up 31. That stores the ammo to the game. As you can see, R30 before we did anything to it was 0. That contains the address of the ammo, -8 because we didn't include D. This is the actual ammo address because it includes D. Then as you can see, R31 is this thing over here, but we're about to replace it with what we wanted, which was the area for the free space in memory. Now, store the ammo address to the free space in memory, which it's going to do. And then, sorry, alarm went off. And then, watch this. R30 and R31 go back to the way that they were before we even did anything. And now, R1, or the stack pointer, is the same thing that it was before we did anything. Basically, what this ended up accomplishing is we used R30 and R31 for our purposes, but it was like we'd never used them at all because we backed them up and restored them. This prevented the game from crashing but gave us free space to do what we wanted. Make sense? If it doesn't, that's okay. You're probably not going to be using stack manipulations quite a bit if you're just making basic codes. Though, to tell you the truth, I manipulate the stack a lot. And the reason that I do is because I always find myself chucking things in there and out of there for some reason. And I'm always needing a lot of space to do what I want to do. Okay, so let's come back to the reading view here. All right, now you've reached near the end of the video. In this part of the video, we're going to be putting everything together. What do I mean by that? In the same function, we're going to use compares, branches, pushes and pops, loads, and stores. We're going to do the whole 9 yards. We're going to put everything we've learned together, and it'll be great. Why are we doing this? A lot of the times, I say sometimes here, but truth be told, it's a lot of the times, the health instruction that writes to your health ends up writing to the enemies too. So if you make an infinite health cheat code, you might find that the enemies are also getting infinite health too, and that kind of ruins the fun of it. Likewise, if you make an insta-kill, you might find yourself getting insta-killed. So, you gotta find some way to make your code be able to tell the difference between you and the enemy. And there's 2 good ways to do this. Both of them are usually near the health value itself. Usually, the player's current HP and their maximum HP are stored right next to each other. And the player's max HP is often a unique value that occurs in no other enemies, allowing you to differentiate between friend and foe. For instance, let's say there's a game where you have 400 HP. Some of the enemies you encounter have 10 HP, some 20, some 100, and maybe the bosses have 1,000. But no other enemy in the game ends up having 400 except you. So what you can do is make your code search for the 400 and then say, okay, if the 400 is there, it's us, and if the 400 is not there, it's the enemy. And then kill the enemy accordingly and keep yourself give yourself infinite life accordingly as well. Another tip that you might also see, and this is the tip that I'm going to be showing you in a minute, is that even if maximum HP isn't stored near current HP, there's often a value in memory near the current HP that is always one thing with enemies and another for you. This isn't always true though, and sometimes this means you can't really make your code differentiate between you and the enemy. But in the case of Borderlands 2, the game we're about to do, you can differentiate. So let's show you exactly how to do that. So as it turns out, here we have the load instruction that controls the visual that you see in game. When you see a health bar pop up, this is the instruction that's doing it. As you can see, your current health is stored at R10 plus 6C. It turns out that R10 plus 60 contains a value that is always 0 whenever it's the enemy and is always greater than 0 whenever it's you. We can exploit this to our advantage to allow us to insta-kill enemies and leave ourselves unscathed. So let's do that for a second. As I said, we're going to have to combine all the skills we've used in one. So I'm going to copy my stack manipulation right here. I'm going to copy this. I'm going to begin the code with it, end the code with it. And then our code is going to be in the middle. So to kind of show you how to look around, I'm at first going to take a look at our health. And I'm going to set an execute breakpoint. There are several enemies in the area, by the way. So this is going to hit up with both mine and the enemy's HP values. Okay, read breakpoint is set. Execute breakpoint is set. And as you can see, the game immediately triggers the breakpoint as expected for a read breakpoint. It's not surprising that they trigger immediately. Okay, so R10 plus 6C gets us where our current HP is. Okay, so add 6C, that's 8C. I probably could have just done that in my head, but it's early in the morning and I am not completely here right now. So I'm not going to do that in my head. Okay, so this is our HP. You can see that there are values ahead of the HP and behind the HP. To go behind, you just subtract. Interestingly, this ends up being a non-zero value right here. And we're not looking at any enemies right now, so it's likely, but we are looking at our health bar. So it's likely that, that this is us that we're looking at. And as you can see, not 0, exactly like I said. So unpause the game, and now I'm going to go and look at an enemy. I'm going to get it in my scope and in my sights. And then I'm going to re-enable the breakpoint. As you can see, the game freezes immediately. Let's see if it ends up being the same thing. 494D AC20. Okay, it's the same thing. I'll let the instruction trigger one more time. well, 2 more times. And I bet you that's the HP of the enemy right there. So let's take this 6C. It's probably going to be AC. See, I can do this in my head when I'm paying attention. 49 E2 EC. So plus 6. 6 is A. AC. Boom. That's the enemy's HP right there. Now, if we minus C, as I said, I found that it was at 60. Look, that's 0. I bet if I set this to 0, the enemy drops dead. Poke. Undo the breakpoint. And then enemy drops dead. So as you can see, there was a difference between self and there was a difference between the enemy. So now that we know what code does this, let's write something that can tell the difference. So remember, as I said, at around 0x60, you find a value that is 0 in enemies, but not in you. So 0x60, and let's see the instruction that we were using again, because I totally forgot. It's this. So first off, I'm going to let the load run first because I don't want to mess with the visual value. So, okay. That's going to load the comparison value. Now, compare word immediate, R30 to 0. And now what I'm going to do, if it's not us, it's self. But if it is the enemy, then I'm going to execute the following code. RLI 31 OX0, 0 for a kill, STR R31 OX6C to write to the health, and R10 to write to the enemy. Be back. And how am I going to do this? Well, I'm going to skip over the write. So I type in self, do a colon. So if this is the self, if this is us, we skip the kill code. If this is the enemy, the kill code doesn't get skipped and they get killed. So usually I would input this in the form of a code cave and show you me adding it to the game. I'm not going to do that. I'm instead going to loan a trader that's going to do it automatically to show you what kind of stuff you can make now that you've learned all of this. But before I do that, let me prove to you that this compiles and is like actually workable code. Oh, something weird. Visual Studio notes the register as FR1. If you type in FR1 in this, it's going to fail. Just remove the R. Same thing for 60, like if it says 6CH, type OX6C instead and it'll work. You have to do things a little differently to get this to work. Sorry about that. But yeah, as you can see, interestingly enough, instead of having to actually write how many you wanted to jump, like in this case, I would jump 2 instructions over, so I would jump 8. I would jump the PC. Well, actually, I would jump it by C. Jumps 1, jumps 2, jumps 3. So I would do B and E OXC. But considering that we're able to write labels in this tool, you don't have to calculate the distance. The tool will automatically do it for you. And as you can see, yeah, there's the C that I was talking about. Anyways, that shows you the code works. Enough of that. Let's actually see it in action. And instead of writing it in, I'm just going to use the tool because I'm lazy. It is strange that someone as lazy as I has enough time and patience to do this. I'm going to connect. I'm going to set to Insta-Kill. And considering it's the visual address, The second the visual for the health bar pops up, the enemies are going to die. So when I look at them, they're going to drop dead. Boom. They just die like that. Boom. Boom. And then if you take a look, I jump on my own grenade. I end up being completely fine. So yeah, that kind of shows you what you can do with all this. Now back to the PowerPoint for one or two more notes before I leave you off. So, what you've learned in these videos will transfer over well, not only to just work for the 360, but work for other consoles too. The processes of finding a memory of value is basically the same in every console. So the processes that I showed you in the first video are done with every console, basically, to find things. But instead, you'll find that consoles often use different tools. Xbox 360 used PeekPoker and XCE tools, whereas something like the Wii used a combination of Gecko OS or programs like WeRD. Interestingly enough, the PowerPC programming language not only is on the Xbox 360, but also on the PS3, the Wii, and the Wii U. As a result, you're actually able to write code for those now as well, assuming you followed through with the ASM tutorial. Once again, though, different codes are used. We use Visual Studio 2010 to set breakpoints, whereas for the Wii, once again, you might use something like Gecko OS or WeRD. And then finally, code keys are necessary in pretty much any assembler code that you make. You're almost never going to have room to write functions in just what's already given to you by the game. So you're going to have to find free space, go into it, and go out. All right. In the next video, I'm going to show you how to create trainers, which are mod tools, RTE tools, kind of like the ones that you just saw what I did in the end. Stay tuned. All right, it's been me. Take care, guys.